All right, 5.5. So today we're going to take a look at what happens when we have bases that don't have e in them. All right, so when we worked before, we worked with base e functions. We're going to actually take functions now that have the same kind of form, a few features of them. So we've got a function that has a positive base, and that base is a real number. And we need that base to also not be equal to 1. Okay, so positive but not 1. Then we would call an exponential function with base a something that looks like y equals a raised to the x power. This is actually defined as that a to the x is equivalent to e to the natural log of a times x. And we'll come back to this definition in a little while. I don't ask definitions on tests, so it's not something you need to memorize, but that's what the definition looks like. And the logarithmic function is very similar. Again, we've got an a value that's greater than 0. A is a real number, and it's not 1. Okay, so all those details are the same. Then if we have a logarithmic function, that would be y equals log base a of x. And again, that's defined to mean, that is, if you have the log base a of x, that means 1 over the natural log of a times the natural log of x. The point when we're going to come back to these is actually what happens when we talk about their derivatives. Okay, that's the only part that will apply, or well, we'll use this information, I suppose. What I want to show you next is a few of the logarithmic issues. So first issue is that any of the properties we had for natural logs, for instance, you had a property that said something like the natural log of a plus the natural log of b is equal to what? Natural log of a times b, because this is addition. And if it were subtraction, it would be division, right? All that still applies. So it doesn't have to be a natural log for that to work. Any log will work there. So that instead of writing ln, I could have written log base 2. Okay, so I could have said log base 2 of a and log base 2 of b, and it would still have the same property that this then is log base 2 of ab. Okay, so all those same rules apply. None of that changes at all. But there are some additional properties that are helpful to know, and the first one actually relates the two on the previous screen together. That is, it's going to relate this y equals a to the x, with this y equals log base a to the x, log base a of x. And those are related as inverse properties. They are inverses of each other. So y equals a to the x. Does anybody know what IFF means? Have you seen that before? It means if and only if. So write it out if you're not sure you're going to remember that. But IFF means if and only if x equals log base a of y. And we talked about this property last time, and we drew what I call a scorpion tail to draw it around to sort of show the relationship on how to change them from each other to the other one. But it happens again here, just like it did with the natural log, it happens with the log. Okay, so that property stays the same. Another one, and some of you encountered this with log properties when they're natural logs on your homework. A couple of you asked me some questions in my office. If you have a base a, and then you have that raised to the exponent of a log base a, then those two are inverse properties. They're inverse operations, and that simply equals x. You can write that down here as though it's the whole thing, because it is. So some people sort of think of this as this a here and this log base a here, they cancel out. Right? They're inverse properties of one another. So whatever is left right here, be a number or a variable or anything right here, we end up with that piece and only that piece left. Okay, that's an inverse property for logs and exponentials. And the third one is very, very similar to that. It says if I have log base a of a to the x like this, that also is equal to x. Again, that log base a and that a to the x, those are inverse properties. So the exponent only, whatever the exponent is, in this case it's x, remains. Okay. We need those. We need them to be able to simplify expressions, because if you simplify expressions before you take derivatives, your derivatives are often easier. We're also going to need that to solve expressions, which is actually where we're going to start. Okay. So the first thing we're going to take a look at is we're going to take a look at a log equation, and our goal is to solve for the variable. And the variable in this case is the variable b down here. And I'm going to do it like I did last time with my scorpion tail, because I think that that's a great visual. It at least helps me, and if it doesn't help you, that's okay. You can do it a different way. We start with the base, whatever that is. In this case, it's base b. And if you follow the arrow around, you get to 3 first. That is the 3 you encounter before you encounter the 27. So the 3 is the exponent on b. The 27 where you land is what you're equal to when you're changing that. You may be able to look at this and tell me what the number is. Sometimes you might not. If you didn't know what b is simply by looking, how could you find it right now?
Take the cubed root.
Take the cubed root. So what is, in fact, the cube root of 27?
3.
It's 3. And you might have looked at that and said, oh, what number times itself 3 times equals 27? And you're doing a cube root as you think through that. B is 3. Any questions on that one? Okay, let's try another one then. As always, they're going to get a little harder. What's harder about this one than the last one? I think somebody said I've got 2 logs. What else did I hear?
Addition.
There's some addition of those logs involved, and I actually have one of the insides of the logs also has subtraction, right? Mm-hmm. So I got several things going on. First, let's deal with the fact that this has addition of logs. I told you all the log properties apply, so when you've got addition of logs, you can combine them how? Multiplication. Now, you're not actually multiplying the logs, but you're multiplying the part that's inside of the logs, right? So the inside of the first log is x, and the inside of the second log is x minus 2. So those are the pieces that get multiplied. I'm not multiplying logs, right? I'm multiplying what's inside of the logs. And they're still equal to the number 1 on the right-hand side. Everybody good so far? Excellent. Now what?
The scorpion.
We're going to do a scorpion tail. I will anyway. So it would look something like this. So I've got 3 as my base. What's next? To the first power. And this equals x times x minus 2. Once you get it to this point, this is algebra, right? And actually, this whole piece is algebra, but this is an algebra that you would have done in high school. Right? This is algebra 2, okay? So what do I do next? I have to distribute. So avoid any kind of temptation to sort of set each of the x and the x minus 2 equal to something. That is a property, but it's a property only when it's equal to 0, and right now this thing's equal to 3. So I do need to distribute. I have 3 on the left, and I have x squared minus 2x on the right. Now what?
Move the 3 over.
I can move my 3 over. So this is going to be 0 equals x squared minus 2x minus 3. Now what?
Factor.
Factor. So I need to factor this. A wonderful tool from algebra. How does this factor?
X minus 3x plus 1.
Good. X minus 3x plus 1. Now what?
Put each one equal to 0.
All right, so we're going to put each one equal to 0. So I have x minus 3 equals 0, which gives me x equals 3. And I have x plus 1 equals 0, which gives me x equals negative 1. Now, so these are 2 potential answers. But I have to see if each one would work. And I could have neither of them work. They could both work, or I could have one work and the other one not. So what do I check? Well, I check the original equation that I started with, way back up here. Okay? I need to check right there to see if they work. In particular, what am I looking for? Well, I'm actually looking at whether or not each individual x value can be put inside of a log, whether it'll work. I'm starting with x equal to 3. Can I put a 3 in right here? Yes, I can. I can have a 3 inside. Can I put a 3 in right here? Yes, I can. Now, that means 3 is going to work, so I sort of check marked this. This one works. What happens with -1, however?
You can't take a negative.
I cannot have a log of -1, natural log or any log. So there is no log of -1 allowed. What that means is that this value right here is what we call an extraneous solution. And you have to check for those. You have to make sure that something that you did along the way didn't create a solution that really isn't one. And that's essentially what an extraneous solution is. That the work that you did with algebra along the way created something that didn't really work. So there's actually only one solution to this problem. X is equal to -3. So you don't have to write extraneous. I do want you to know what that word means, but you don't have to write it down, but you do need to cross it out. That is that you've checked it and it's not going to work. So there's only one solution to this problem, x is 3. Any questions on this one? Okay, let's try one more of these. Looks a little bit different yet. I don't see any logs in this one. I actually see an exponential to start with, right? Okay. In fact, this actually should look like something you've seen before, because you have seen problems like this before. Does anybody remember what this is an application of? Can you tell?
Like compounding.
It is compounding. Do you know what it's compounding, Parker? It's okay if you don't, but...
Like continuous or is it?
You're close. This is actually compound interest. It's not continuous, it's daily, because you see that 365 days in a year. This is continuously compounded interest. Actually, what this problem would have resulted from is from somebody asking you to find the doubling time for something. Okay? I don't care if you know that necessarily, but that's where it came from. Okay? So, simplification. What can I do to simplify this? What can I do to solve this? What am I going to do in this problem? Any suggestions? Well, I'm not asked to find a derivative. Just solving. I just need to figure out what is t. Okay, everybody's very much overthinking this. That's good news. Well, sort of anyway. Can you not just combine these pieces together first? It's all numbers inside, right?
Yes.
Yes, you could combine them. So everybody grab your calculator out because you're going to need it to find your final answer in a minute here anyway, because this is definitely the kind of problem that results from an application. What I'd like to know is I'd like to know the decimal. We'll write down, I don't know, like 5 decimal places. In your calculator, you're going to leave it unrounded though, okay? So I want to figure out what is 1 plus 0.1 over 365. It's not much more than 1, so... 0.0027. Okay. Now your calculator has more after that, right? Yeah. So leave your calculator put. We've got to stop here at some point. So I picked 5 randomly. 5 decimals. I still have 365 t as my exponent. But this looks better than it did before. I mean, it may have an ugly decimal expansion, but at least I don't have addition and division involved, right? I'm making progress. However, I haven't made the biggest progress that I need to make. Right now, I've got a variable in an exponent.
Change it to a log.
You can change it to a log. And we did that both when we talked about taking derivatives. We did it for that purpose. And we talked about it when we just talked about simplification. So I'm actually going to take the log, and you can do natural log, you can do whatever log you want. I'm going to do the natural log of both sides because I can. I have a choice, so I'm going to pick natural log. Okay? Why in the world is that helpful, Michaela? Because you told me to do it.
Because it'll bring the exponent down.
Property of log says that if I have an exponent, I can bring it down. That's good news, because if I can get the exponent down, I can solve for it. So I've got 365t natural log of 1.00027 with some more stuff that's still on your calculator screen equals the natural log of 2. Now what? We're going to isolate t. Can we do one more thing before we isolate it that might just be handy for your calculator to do? Right. We can combine these pieces all together. So you've already got that 1.0027 in your calculator, right?
Yes.
So I want you to hit natural log, and then I want you to hit the second button, and then the ANS button, which is the negative key. Can everybody find those keys? Do you know what I'm talking about? I know some of you have worked with the calculators longer than others, so I want to make sure everybody's on the same page on that. After you do that, hit enter. That's going to give you the natural log of the 1.00027 extended decimal expansion, right? And then hit times 365. We're just going to keep going with 5 decimal places. Your calculator is going to keep it exact. But you're going to tell me, what do you have correct to 5 decimal places when you did that?
0.09999.
If I have 5 decimal places, this is what I have?
Mm-hmm.
Excellent. Everybody has the same thing. Okay, so again, you're not actually rounding, but you got to write some condensed form down. This will work. Now what do I need to do?
Divide natural log by that.
Yes, so the value you have in your calculator right now is going to divide to the other side. Do not actually enter negative natural log of 2 divided by 0.09999, whatever. That's not what we want to do. I want you to hit natural log of 2, and I want you to close that parenthesis. Because your calculators, most of them force you to put parentheses around the natural log of 2. Then I want you to hit division still before you hit enter, division. I want you to divide by second answer, second, and then the negative key, that ANS key. That will take the previous answer you had with all of its wonderful decimal expansion on all of its glory, unrounded, yeah, and it will use it as a division factor, which is great, because then you don't have to type it all in. And you don't have to round it, so that's good too. That will actually give you a time, and we're going to go with time. We're going to go 3 decimals on all answers unless otherwise indicated. Okay, so what is the decimals to 3 decimal places for my answer here?
6.932.
And we already know that's years because we kind of talked about the context behind this problem. But that would be my answer without context that we're going with. Okay? All of that is usually taught in a college algebra or a college, like maybe an algebra 3 or pre-calculus class in high school. But that's how you can use your calculator to help you out with it too. Any questions on this one? Okay. We're going to move on into the calculus part of this then, and we're going to talk about derivatives. Okay? So we already talked about some of the conditions. So you remind me, what were my conditions? A was positive. What else?
Cannot equal -1.
Okay, it's not equal to a 1, yeah? And it's a real number. Okay, so those are the same conditions that we had before. And we're going to take a look at the 2 derivatives we're talking about. So if I have f of x equals a to the x, or y equals a to the x, if you want to write it that way, then the derivative of this is a to the x. Okay, so that's kind of like the e to the x rule, right? The derivative of e to the x, e to the x. But then you have to multiply that by the natural log of a. You can put the times natural log of a behind it or in front of it. It doesn't make any difference, kind of like when we do our other rules, of course. And I want to take that idea and I want to go back to where I did that definition to show you where that piece is coming from. So take a look at how we define this. A to the x equals e to the ln a times x, right? Okay. So if I want the derivative of this thing over here, I need the derivative of e to a power. The derivative of e to a power is e to that power. So this piece right here is going to be part of the derivative. But then you have to take the derivative of the exponent. And what is the derivative of the natural log of a times x? The natural log of a. So that's where that other piece of this formula is coming from. So you have the same derivative of a to the x is a to the x. But then you get the times the natural log of a from that derivative definition, or from that definition of a to the x from before. Okay, and the second one works the same way. We've got f of x equals log base a of x, and the derivative. So think with me for a moment. What was the derivative of the natural log of x? 1 over x. That's going to be part of the derivative here too, 1 over x. And then we're going to have that, times the derivative of 1 over the natural log of a, natural log of your base. And again, you can write that in another order if you want. You can write that as 1 over ln of a times x or some variety. Okay? So we're going to do some derivatives now. Again, this is not on your basic skills quiz, so you don't need to know this rule by heart or anything like that. But you do need to be able to work with it for sure. All right, so if we've got a function, I always like mixing notation. Some of you get really uncomfortable with this. You're in my office still. So I'm going to pick on Taylor a little bit because she was in my office and had a similar kind of question to this. Taylor, when we look at this, what's the first thing we should see? A product rule. Okay? Some of you are still having difficulty sort of identifying that from the get-go. This is a product rule. I have a t squared and I have a 2 to the t, and they're multiplied. So I'm going to have a product rule here. Now, part of this product rule, namely t squared, you've worked with that derivative before. The other part, 2 to the t, is the newest one that we just listed. I mean, some of you still may have worked with it before in a different class, but you haven't worked with it here yet. So we're going to do the product rule. When I do the product rule, I do the first part and I rewrite it. Don't have to do it that way, but that's how I handle it. Then I need the derivative of 2 to the t. Now that's the new rule. So what's the derivative of 2 to the t?
2 to the t is natural log 2.
2 to the t, natural log of 2. Perfect. But I'm only half done because this is a product rule. The other half of the product rule says that I need to take the derivative of the first piece. So what is the derivative of t squared?
2t.
2t. And then what do I do?
2 t.
I rewrite the 2 raised to the t. Now you need to be really careful on 2 counts on this problem. Number 1, your t's need to be careful not to look like plus signs. That's why I put the little curlies in the bottom of my t's when I do math. That is not how I write t. I write t's just like you do probably, with no curls in the bottom. But in math, I write them with curls. What's the other thing that you need to be careful about?
Combining the 2's.
Yeah, hang on just a second. We're going to combine the 2's and have to be careful there. But first, what do you need to be careful, Parker?
Keep the exponents and the regular t.
Yeah, and that sort of catches me by, surprise sometimes too if I'm not being real careful, right? So those exponents need to be sure they really look like exponents. And when it's not an exponent, it really needs to not look like an exponent, okay? All right, so Michaela, did you have a suggestion on how to simplify with this? Is that where you were headed on this?
Oh, no, I was talking about, don't misread it and think you could combine the 2t and the 2 to the t power.
That's true, and that's part of that issue of making sure that we have the exponent differentiated from the base, right? Not making it look like they're on the same sort of level. All right, so as I'm taking a look at this, there are some things I can do to simplify, and it's all about factoring. What can I factor out of each of those pieces? 2 to the t is one of them. What else? A t. So I'm going to put the t in front, partly because of what Michaela suggested. I don't want it to sort of look like it's going to combine with something it's not. So I'm going to factor out a t and a 2 to the t. If I factor that out of my first piece here, what's left?
T natural log t.
T natural log what? 2. Yeah. And if I factor that out of the second piece, what's left? Just a 2. And unfortunately, that's as good as it's going to get. Not going to get any cleaner or any more simplified. That's the final answer. Okay with you? All right. I bring this one up again because many of you back when I graded 5.1 wanted to approach this in a complicated way. What was the complicated way you wanted to approach this? With a quotient rule. What is the uncomplicated way to approach this?
Log properties.
Log properties. So that's the one I'm going to go with. I want to use log properties. So I'm going to rewrite this before I start. Using log properties, how can I rewrite this?
Log x squared minus 1 minus or log x.
Right. Yeah, we're all in the habit now of saying natural logs. This one is log. Now, let me make a comment. You probably know this, but just in case you've forgotten. It doesn't look like I've got a base on this one. So what is the base understood to be?
10.
It's 10. Okay, good. So when there's no base written down beside it, it's called the common log, and the common log is a base 10. All right, so I'm actually ready now to take a derivative. What is the derivative of log of x squared minus 1? That's the first piece. Erin has the first piece, so it's 1 over x squared minus 1. That's one of them. What else? There's more to it.
Times 1 over the natural log of 10.
Times 1 over the natural log of 10. Okay, so that's still the derivative of the outside part, right? That's my new rule. My new rule says if I have log of a base, and this is understood to be base 10, I need the 1 over whatever's inside times 1 over natural log of the base. Okay, so this is the outer rule. But I've got a chain rule actually going on here as well. Somebody else started to say that too. I need to take the derivative of the x squared minus 1, which is 2 times 2x. Okay, so this piece is the derivative of the outside. This piece is the derivative of the inside. Got to have them both because I do have an inside function here. The next piece is actually easier because I don't have an inside function. I just have plain old x. So what's the derivative of log base 10 of x? 1 over x
1 over natural.
times 1 over the natural log of 10. So far, so good? All right, so I'm actually going to simplify this. The first thing I'm going to do is by factoring out that natural log 10 part, because it matches, right? So I'm going to write that at the front, the 1 over the natural log of 10. And then I can combine the 2x and the 1 over x squared minus 1. So that's 2x over x squared minus 1. And then I have minus 1 over x. Now what?
Common denominator.
Common denominator. What will my common denominator be? Unfortunately, it's simply the two denominators multiplied, right? They don't simplify any, so I'm going to give myself a little bit of space. The first fraction then needs to be multiplied by what? X over x. And the second fraction? X squared minus 1 over x squared minus 1. Okay, looking good. Y prime equals 1 over natural log 10. And we're going to combine. So what is the first one? What's 2x times x? 2x squared. I've got a subtraction sign between them, which is now going to be pushed up into the numerator. And I'm going to have minus x squared, and then plus 1, because I distribute that negative through. All of this is over my new denominator. My new denominator is x times x squared minus 1. I'm trying to think if there's any case, and I can't think of any case where it's helpful to actually distribute that denominator. So you just leave the denominator in factored form. And in fact, you're going to see on this one, things are going to clean up on the numerator as well. So in the numerator of this one, what cleans up? Yeah, those x squareds can combine. I've got x squared plus 1, which unfortunately is almost like the denominator, but not enough like it that it actually simplifies, right? So this is the best it gets here. I have 1 over natural log of 10. I've got x squared plus 1 over x times x squared minus 1. Even if I factored x squared minus 1, which I could, it's x plus 1 times x minus 1, just difference of squares. I can't factor the top. There's not a factoring of perfect squares that are summed together, so there's nothing to do to simplify. All right, the next one. We haven't done one of these in a while. because we're going to use logarithmic differentiation. Do you remember what that word means? What those words mean? It means I have to take the natural log of both sides first. Now, if it did not have that direction, you should still know that's what you have to do, and here's why. What is weird about this problem? There's a variable in the base and in the exponent, which means the two rules that you know about doing derivatives won't work, because the two rules that you know about using derivatives have an exponent in only one location. I mean that's just the gist of it right there. So I have to be able to get that exponent out of the exponent. That 2 over x can't stay up there and me actually be able to make progress. And the way that we get exponents to move locations is we take logs. So that's where we're going to start. We're going to do the natural log of y on the left, and we're going to do the natural log of x to the 2 over x on the right, with the only reason for having done so really to be pulling this down. So far so good? So this is the natural log of y equals 2 over x natural log of x. Now, I do not have an exponent in a variable in an exponent and a variable in the base. I still have two variables, but how are these two variables interacting? What kind of property can I use, or what rule can I use on the right-hand side now? Product rule or quotient rule, depending on how you look at that, right? I think of it as product rule as well, but if you want to change it, you can think of it as a quotient rule, okay? All right, so we're going to treat this as either a product rule like this, or if you prefer, we could think of this as 2 ln x over x and think of it as a quotient rule. Okay, so those are your two choices. I'm seeing people nod that they don't like that quotient rule idea, so we'll stick with the product rule. Okay? All right, so let's start with the left-hand side, however. The left-hand side, I've got the natural log of y. What is the derivative of the natural log of y?
1 over y dy dx.
Good, we've got 1 over y, and then I need dy dx. On the right-hand side, as we've already mentioned, we've got a product rule. So a product rule says I'm going to rewrite the first piece, so that's 2 over x. And now I need the derivative of ln x. So what's the derivative of the natural log of x? 1 over x. Then a plus. Now I need the derivative of 2 over x. So what am I going to do with that?
Bring the x up.
To the negative 1. Right, so 2 over x is the same as 2 times x to the negative 1. Okay, so this is kind of like my little scratch paper to the side, so it'll allow me to think, to write down the derivative. What is the derivative of 2x to the negative 1? Negative 2x to the negative 2. And then what? Times the natural log of x times the other piece of the product. Okay, so we got to do a little cleanup because this looks like a mess to me. We have 1 over y times dy dx. This is actually 2 over x squared, which isn't so bad because if you take a look, then this is actually minus 2 ln x over x squared as well, isn't it? That's kind of friendly. The denominators match. Okay, so at the very least, you can tell me it would be worse. It could be worse, right? It could be worse, okay. There is one other thing that I need to do on this problem after I push them back together, combine them, if you will. What is that thing that I need to do?
Multiply by y.
I need to multiply by y. So this 1 over y is going to be multiplied to the other side. So here I have 2 minus 2 ln x on top, and I have x squared on bottom, and I have times y. This space? No. Okay. And you know what y is because the problem actually started in form y equals. Not all implicit differentiation or logarithmic differentiation has that property. This one did. So I can actually simplify it so that I can write 2 minus 2 ln x over x squared, and I can multiply that by x to the 2 over x. This will work. You might actually see that 2 factored out on top. That's a possibility. So what I've got in brackets there, or in the box there, is fine. You could see this written as the 2 factored out with the x squared on bottom factored out or something like that. And do 1 minus the natural log of x. And, oh, I've got a typo written there. I'm sorry. Nobody wanted to tell me. Let me write that right. 2 over x. And then x to the 2 over x. Some variety of that might be what you see on someone else's paper or written in the back of the book. Okay. Either of those would be fine. Any questions on that one? Okay, so derivatives and antiderivatives as well. So antiderivatives are often just the reverse of doing a derivative, and they are in this case as well. So again, details, what do we have? Well, we have a is greater than 0, a is a real number, and a is not 1. All the same conditions that I had before. We're only going to have one antiderivative rule. The antiderivative rule we're going to have is the antiderivative of the function a to the x. Okay, just like you don't have a closed form antiderivative rule of ln x, that is, if I ask you to do the integral of ln of x dx, we haven't worked with a rule like that yet. There's nothing that we've worked with. We won't get to that till we get to chapter 8. So anytime we saw something like this, we said, well, somehow I got to use a u substitution with the u equal to ln x, and it had some other forms of things in there. So for the same reason, we don't have a rule to work with for this one yet. Okay? So neither of those are happening anytime soon. But we do have a rule for f of x equals a to the x. So if I'm working on this one and I want the antiderivative, that is the capital F of x, right? I still have that a to the x, okay? Just like the derivative of e to the x is e to the x, the antiderivative of e to the x is e to the x. Well, the derivative of a to the x had an a to the x in it, so the antiderivative of a to the x has an a to the x in it. All that happens the same way. But before, when I took the derivative, I multiplied by what? Natural log of a. So what do you think I might do now? Divide by it. Or I'm going to write it as though it's multiplication, but it's division, right? So the derivative the derivative had a times ln a. This one has division by the natural log of a. Okay, just exactly the opposite. And we're going to do a couple. Okay, again, you could write this in a couple of ways. We could go like this. Or you could write it in front. All right, so here we have an indefinite integral, x cubed plus 3 to the negative x. And I was working with a couple people in my office this morning, and we talked about the fact that sometimes when there's u substitution involved, it doesn't involve the entire function. And in this case, we've got that, in fact, going on. The first piece, x cubed, you know that antiderivative. You've been working with that for quite some time. The second piece is the new piece that we're working on in this particular section, and there's a u substitution involved. So let's work with one piece at a time. The first piece, x cubed, what's its antiderivative? X to the 4th over 4. No problem, right? The second piece, however, does not simply look like 3 to the x. It's 3 to the negative x, okay? So technically, we actually have a u substitution going on here. Let me do it. We'll do it over on the side here. Hang on. So my u is negative x, right? What's the derivative of negative x? Negative 1 dx. I don't have a negative 1 in my problem, but I do now. I've got a negative integral of 3 to the u du. All right, so now we're back to where we were before. That is the previous slide where I told you how to deal with a to the u, or a to the x was what it was. What is the antiderivative of a to the x? Well, it's a to the x. So the antiderivative of 3 to the x, or 3 to the u, is 3 to the u times what? 1 over the natural log of 3. Okay, not the natural log of the variable, but the natural log of the number, the natural log of the base. I need a plus c. This is a terrible way to stop the problem because I've got u's and x's all in the same step. For different reasons, of course, and that's okay, but I can't stop there, right? So I would rewrite this as minus 3 to the negative x, and I'll write it all in one step over the natural log of 3 plus c. You do not need to get a common denominator for the 4 and the ln 3. That's just going to muck up the waters and look just worse than it does now. So it's fine to leave that. Any question on that? Okay, we've got one more. I've got the integral of 3 minus x quantity times 7 to the 3 minus x quantity squared. What would you like to try? Well, u substitution is the most popular thing, right? And what would u be? Would it? It's going to actually be 3 minus x squared. And here's why. If you simply let it be the 3 minus x, that takes care of what's in the parentheses, but then your function would still say 7 to the u squared. Well, you still don't have a rule that deals with u squared. You only have a rule that deals with the variable being the only thing in the exponent. So that entire exponent needs to be my u. Okay? Because what I need is I need this to say 7 to the u when I'm done. Make sense? Okay. Now, that's a little different than we've worked with as of yet. So now I've got u as 3 minus x quantity squared. I need the derivative of that. What's that going to give me? Okay, that's correct. Let's talk about where each of those pieces came from. Where did the negative come from?
From the derivative of 3 minus x.
Right. So the negative came from the derivative of the inside. The derivative of 3 minus x is negative 1. Where did the 2 come from?
From the exponent.
From the exponent coming down. The 3 minus x, why is it still there?
The chain.
Because we're dealing with the chain rule here, really, right? And my new exponent is now a 1. I don't have it written there, but it's a 1 because I did 2 minus 1. Everybody good with that? The beauty of this is that that's actually part of your problem, isn't it? 3 minus x and dx, that's my du. Well, part of it. I still need to deal with this negative 2, so I'll divide it to the other side. So I'm going to have my negative 1/2 integral. The 3 minus x and the dx, the parts that are underlined in red, are going to go away then with the du. The 7 is still there, and that 3 minus x quantity squared is my new variable u. Perfect. What's the antiderivative of 7 to the u? 1 over ln of 7. Good. You need a plus c still, right? Okay. I've got a couple of denominators here, so I'm going to pull that ln 7 to the front. So I'm going to write this as 1 over 2 ln 7. And then I'm going to write this as times, or if you want to not write the times, you don't have to, but 7 to the what? 3 minus x quantity squared plus c. This is a perfectly fine way to write this. There's one other thing that you might see happen if you're working with, checking online or back at the book or something, is that you might actually see this written as the negative natural log, 1 over the natural log of 49 times 7 to the 3 minus x squared. Why? You could, yeah, you could write that actually in place of the 1 on top, yes. Can somebody tell me what happened to say that that's the same thing on the second? Right. The 2 that's in front of that natural log of 7, that coefficient of 2, could be written as an exponent on the 7. So that's a possibility as well. Again, I don't care that you do it, but if you looked on something and saw that answer, I need you to know that that's the same thing as you had. Okay? All right, we're going to deal with a couple other small issues. One of them is compound interest, which we had already mentioned a moment ago. And you may or may not remember the exact formula, and you're going to have a couple of applications that are going to call back to this thought. The formula for compound interest looks like this. That is an R as the numerator of that fraction. So that says A equals P times 1 plus R over N to the NT on the outside. Just a reminder about those details. P is the principal. What is principal of a problem? What does it actually mean? It's the amount you either borrow or put into an account. Okay, so if you're talking about taking out a loan, it's the amount you borrow. If you're talking about putting money into a savings account, it's the money you put in. Okay, so it's the lump sum amount that you're starting with, either owing or putting in. R is your interest rate. So interest rate is given usually as a percentage, like 7%. But the R in the problem is not written in the percent form. It's changed to a decimal, so you put 0.07. Time is always given in years. So if somebody talks about an 18-month loan or an 18-month CD rate or something like that, you can't put 18 in for T. You'd have to put in 1.5. So you've got to remember that the T in this problem is always time in years. And then A is the amount you have in the future, like the amount that you still owe when this, 3 years from now and you still owe money on that car. Or A is the amount that you now have in that CD or savings account or mutual fund or whatever. Okay? And then if you have continuously compounded interest, which someone mentioned before as well, that formula looks like this. P is still principal, R is still the interest rate, T is still the time. And there's one variable that I haven't mentioned from the formula. You guys are all flipping the paper and I didn't do it. What in the world is N? Does anybody remember? N is the number of compoundings per year. Okay, so the reason that it doesn't show up in this formula down here is because it says it's continuously compounded, which means all the time, right? Continuously all the time. When it shows up in the first formula, that's when you have things where it says compounded monthly. So N would be 12. Thank you, 12 times a year. Monthly means 12 times a year. Compounded quarterly. Every 3 months, which would be 4 times a year, right? 4 times a year. Daily, we saw this one? 365 and so on. Okay, so we can use any of those numbers in place of where the N is. Notice N's in there twice. It's the denominator and it's part of the exponent. And that's part of the problem we saw when we had that 365 involved in the early part of this lesson. All right, last thing we're going to look at is a logistic function. You might not have seen this before. It is something that is sometimes addressed in an algebra course, but not always. It has this basic form. That's a bx as an exponent, negative bx. I've put in here the pictures of what this looks like. These are logistic functions. They're functions that increase really rapidly or decrease really rapidly for a while, and then they level off. So what you kind of want to imagine is if you introduced, for instance, deer into a new forest or foxes into a new area. At the beginning, there's lots of resources and they have lots of ability to multiply and everybody has plenty of food, right? And the hunters haven't come yet or whatever, right? We've got lots of resources and little concern about ability to survive. But eventually, you keep multiplying, multiplying, and multiplying whatever that animal or issue is, and we max out what we can actually support. Either animals leave to go to another location, or they can't find enough food to survive, right? And so you have this leveling off feature. That's the first picture that you're seeing happen. A couple of things about these graphs happening here. L is the limiting value. It's how much you can actually support in whatever population you're talking about. The A and the B, in particular the B right there, notice the B has a negative in front of it. Do you see that? It's kind of weird. So if B is if B is greater than 0, like in my first picture, the exponent's actually negative. Right? Because B is positive and it's got a negative in front of it. So B is actually negative, or I'm sorry, the exponent's actually negative here. So this is a negative exponent. And the same kind of issues going on when B is negative. If B is actually negative, then you have a negative times a negative exponent. This is actually a positive exponent. So a positive exponent actually is a decreasing graph, and negative exponent is actually an increasing graph because of the formulas that we're working with in this one. And I think you have like one problem that deals with carrying capacity. Limiting value logistic functions. Okay.